All right, so we left off on Thursday in 13.3, measures of relative position is what they call that section. But the idea is you have a set of data, bunch of numbers. You want to talk about where a particular number in the data set lies relative to the other numbers in that data set. And the main way that we do that is with that thing called a z-score. The z-score has a little formula. The z-score is equal to the number of interest, x, minus the mean over the standard deviation. So the idea is usually the number of interest is given to you. The mean is given to you, standard deviation is given to you, so we can calculate this z-score. And sometimes the notation looks a little different, just depending on whether you're talking about a sample or a population. Just because you're talking about a population, you use the Greek letter mu for the mean, as opposed to x bar from a sample. They also use the Greek letter lowercase sigma for standard deviation from a population, where they use an S for a sample, but the idea is the same. You take the number of interest minus the mean, divide by the standard deviation. So we did a few of those. I want to do one more before I continue on. I have a couple other measures of relative position in this section. What I want to do is right. What the z-score does, it allows you to compare numbers in different data sets. I was using that example. Suppose you got an 80 on a test. 80 by itself sounds really great, but an 80 would be really great if the average was like a 60. If the average was a 60 in a class and you got an 80, you did well above average. Really good. But suppose you got an 80, but the average actually was 90. Suppose the average score was a 90 and you got an 80. Well, then it sounds very different because actually you did below average. It's this z-score that allows us to compare those different situations like that. How does the 80 compare to the average? And you divide by the standard deviation. And so that's what they're wanting us to do in problem 8, is compare these different scores, different tests, and determine which one is highest relative to the other scores in that class. Anyway, they say here in problem 8, this first scenario, there was a 66 on a test where the mean was 72, the standard deviation was 7.6. What is the z-score there? I'm going to calculate the z-score so I can compare it to these other situations. And tell us the score for scenario is 66. Mean 72. Standard deviation was 7.7. So what was the z-score? So I need to plug it in the formula. Take the score of interest, 66, minus the mean, 72, divide by the standard deviation, 7 point. Actually, 7.7, not 7.2, 7.7. So it's negative 6, 7.7. I divide those, negative 6 divided by 7.7, negative 0.77922077. I've got to do these for all of these. Got to do this calculation for all these. One thing I want to point out though is it's negative. And all that means is it's below average. The 66 is below the average. So it ended up being a negative z-score. Anyway, the next one said there's a score of 118. The mean was average 130. Standard deviation 18.7. Calculate the z-score. Take the score of interest here, 118, subtract the mean, 130, divided by the standard deviation, 18.7. Negative 12 over 18.7. Add those. Negative 12 divided by 18.7. 0.64171123. Again, it's negative because this score was below average, it was below the mean. The z-score was negative. Third situation, score of 617. 617 with a mean 720. Standard deviation 117.5. Third time here, just different numbers. The mean score of interest 617, mean 720. Divided by the standard deviation 117.5. It's negative 103. 17.5. Find those. Negative 103 divided by 117.5. Negative 0.8765974. All right, so again, what this does is it allows us to compare scores in different scenarios where the mean and standard deviation are different numbers. The question though is, which of the following three test scores is highest relative score? Which one's the highest? Trick you in their negative. Which one's the highest and which one's the biggest? It's tricky, but to make it more obvious, I can plot these on the number line. Got 0 here, let's say. And negative 1 put out here. This negative 0.779, so on, is, I'll break this in tenths. Negative 0.1, 2, 7, 8. So the negative 7 or 0.779, roughly right about here. The negative 0.641711123. Between the negative 6 and 7, a little closer to the negative 0.6. roughly right about here. Then this last one. Negative 0.87659. 5745. Between the negative 0.8 and 0.9, but close to the 0.9. Here. So which one is biggest? The bigger numbers are to the right, smaller numbers to the left. So the biggest one, this one. Blue. This one is the biggest. Might be tempting to look at this and say, this is the biggest. Actually, that's the smallest. Because they're negatives in the way it's kind of backwards. That is the biggest one. So that came from the middle one. 118. It's actually the highest relative mean standard deviation. So anyway, continuing on. Most of the problems have to calculate z-scores. But then, starting in problem 10, they want us to figure out something different on the z-score. Wants to figure out something called a percentile. Number 10 says on a reading test, Shaylin's score of 455 was higher than scores of 4,279 of the 7,201 students. Find the percentile. So in a way, it's still talking about position of that score. Just like with z-score, it's talking about relative position of a score relative to the mean and standard deviation. Here, just relative to the scores overall. On the percentile. Okay. Here's the definition. Percentile. He represents a number. 70th percentile, something like that. A value X is called the percentile of a data set. Provided B%, again, B represents a number like 70%. The data are less. So if you scored the 70th percentile, what that means is that score, your score is higher than 70% of the people that took the test. It's higher than 70%. When they say it is 70%, it's less than that score of interest. There's a little formula for it. Percentile of score X equals data values less than X. Divided by total number
Added values. And then you multiply by 100% to make it a percent. So in problem 10 here, Shaylin scored higher than 4,279 people. So 4,279 scores were less than hers. That's the number that goes in here. And then they say, altogether, 7,201 students took the test. So that's how many took the test altogether. That's the number for the development. So the percentile is calculated by just dividing those. Percentile. $4,279, 7,101, and then times 100% to make it a percent. So when I divide these, I get a decimal number. It's less than 1. 4,279 divided by 7,201. 0.942233025. Then times 100% to make it a percent. Just moves the decimal point to the right twice. 6%. This is one of those step-by-step problems, so doesn't tell you how to round the answer here at the beginning. But in the others, they usually say nearest percent, so nearest whole number. So 59%. Shaylin's score is in the 59th percentile. Number 11, similar. Except we have to do a little bit more first. Anyway, 11 says on the placement examination, Rick scored lower than 1,151. Rick scored lower than 1,151. Other people. Altogether, there were 12,670 students who took the exam. 1,760. Wrote that backwards. 12,670. The reason I can't just go straight to percentile formula here to try to calculate the percentile is I need the number of scores that were lower than Rick. But they're telling me Rick's score was lower than this many scores. So to say that the other way around, there were 1,151 scores higher than Rick. And what I need is lower than Rick. If you could imagine kind of drawing a picture of all the scores, there's all these scores that were lower than Rick's, then there was Rick's score. Then there were a bunch that were higher than Rick. They're telling us right here is Rick scored lower than, Rick's score was lower than 1,151. But what I need is this number. How many were lower than Rick? what I need to do is subtract. But also, don't, yes, sir. Notes? No, I did not. Okay, comes up. So. See, I'm saying there was 1,151 scores that were higher than Rick. There's Rick's score as well. And then all together, there's 12,670 scores total. And what I need is how many scores were lower than Rick's. Calculate the percentile, so I need to subtract. So the number lower than Rick. Would equal to 12,670 minus, I need to subtract how many were higher than Rick. And I also need to subtract the one score that was Rick's itself. I need to subtract 1,151 and one more for Rick's score. $12,670. It's 1,151 minus 1. 11,508. So there were 11,518 scores that were lower than Rick. So now I'm ready to calculate the percent. Take how many scores were lower than Rick's? 518 divided by how many that were total? 1,670. Multiply times 100% to make it a percent. First divide these. Zero point 9090765 times 100%. Just means the decimal point to the right twice. $90.9076559. Then I say rounded to the nearest percent, nearest whole number. We're now up to 0, but then it seems a 9, so 190. So percentile 91. Number 12, it's kind of backwards. Both those first two problems, they gave us numbers, we needed to figure out the percentile. In 12, they give us the percentile. And when it's figure out, it's how many students scored lower than Kevin. It says Kevin scored at the 70th percentile. So 70th percentile. On a test given to 9,880 students. 9,880 students total. How many students scored lower than Kevin? So formula is calculate a percentile, you take the scores that were lower. The total number of scores times 100% to make it a decimal. This time what I know is the percentile, 70. Scores that were lower, we don't know. I do know the total number of scores. 9,880.
if I create this little equation, and I can solve for the number of scores that were lower.
First, I'm gonna divide both sides by 100. Might be easier to say, multiply both sides by 1/100. It's equivalent to dividing by 100, but just looks better if I write it that way because it's a fraction over here. Anyway, though, just cancel out on that side. Over here, 1/100 times 70, 0.7. Now multiply both sides by 9,880, 9,880. Just cancel. Then the number of scores that were lower, multiply those, 0.7 times 9,880. 6,960. 6,916 scores were lower than, excuse me, Captain. There's one more measure of relative position. Z-scores used the most. Percentiles used often. Probably heard of percentile even before this class because often they are used with scores like ACT score or GRE test and different things of that nature. Anyway, the third measure relative position is called the quartiles. Quartile itself, it's got the word quart in there, quarter of the data. So quartiles split the data up into quarters. Here's the official definition. The three numbers represented by Q subscript 1, Q subscript 2, Q subscript 3, a partition, a ranked, that's it. Pause for a second, because right there it's already sounding confusing, I think. So partition means splits them up into groups. For ranked data means they're in order. So they're put in order from lowest to highest. And then they're broken up into groups, partitions, based on whatever these groups are. Into 4 equal groups. Are called the quartiles. Data. They've got a simple example in the book. I'll write down here. They say here's the data set, and it's ranked, meaning it's ordered 2, 5, 4, 5, 8, 11, 12, 18, 22, 23, 29, 21, 45, 23, 91, 104. So we got this big group of data ranked. We're going to pick 3 of these to split the data into 4 groups. This one here, that 11 is the Q1. 29 is the Q2. 104 is the Q3. You can see what's happening here. This big data set, these numbers that are labeled here, Q1, Q2, and Q3, they're breaking the data into 4 groups. So it takes 3 numbers to break it into 4 groups. Each group in between these Qs has 4 data values in it. There's 4 below the Q1s. There's 4 in between Q1 and Q2. There's 4 in between the Q2 and Q3. And then there's 4 above the Q3. So these Qs are breaking the data up into 4 equal. Our goal, of course, is going to be to find those. We're given a data set, how would we find them? There's a procedure. And the first part of the procedure actually relies on the fact that this Q2 already talked about. We didn't call it Q2, we call it the median. The median is the one in the middle. I look at this 29 right here. There's 9 numbers before, 9 numbers after. It's exactly in the middle. So Q2 is the median. Procedure says, rank the data, put it in order. It's not already in order, right in order, smallest to biggest. Step 2, find the median. Median is, this is the second quartile. Step 3, first quartile. Q1 is the median. Of the data values. Less than Q2. There's more to add there, but I just want to point out. Suppose we have this data set. We're trying to find the Qs ourselves. We find the median. We've done that before. Then you look at just the numbers below that. And you find the median of that. Middle of these numbers. So the middle of those would be right here at 11. That's the first one. The thing I still need to add there is for finding the Q3, you look at the numbers above the Q2, find the median, that half of the data. This is the third quartile. Q3. The median. Data values. Greater than the Q2. So you find the overall median. It's the Q2. And you find the median of the lower half. It's Q1. Find the median of the upper half. That's Q3. Number 14. Wants us to find the quartiles. Says a survey was given to 18 students. One question asked about the one-way distance the student had traveled to attend college. Results in miles are shown in the following tables. Use the median procedure for finding quartiles to find the first, second, and third quartiles from this map. Got these numbers here. Find the three quartiles. So the first thing we need to do is put them in order. Follows the base. 5, 7, 11, 219s, 11, 219s. The 30s, let's see, there's 35s. Oh, there is one in difference. 29. 29. Now the 30s, it's 35. 39. Another 49. And 30. 35. 339. 40s. 47. 49. 50s. 8, 5, 7, 9. 5, 7, 12. And there's a 69, 75. 9. They're all in order now. Now I need to find the median, middle number. There's 18 numbers, because I said 18 students, but just to count to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 numbers. Whenever there's an even number of numbers, there's not just one we can point at and say it's in the middle all by itself. If they're an odd number, good, but with an even number, there's not. Because if I point at this one, it's got 1, 2, 3, 4, 5, 6, 7, 8 before. 1, 2, 3, 4, 5, 6, 7, 8, 9 after. So it's not the middle by itself. If I point at this one, it's the same thing, but the other way around. There's 9 before and 8 after. So I have to take the middle two, take those two together, 8 before and 8 after. So those two together are the middle. So the median is the average of those two. So the median is 39 plus 39, which is 78 by 2, which is 39. So the median is 39. The median is the second quartile. So it's 39. Now what I do is I break the numbers in half. the median came from averaging these two, so I break it in half right there. All the numbers before,
All the numbers after.
first the ones before. 8 numbers. 9 numbers.
So there's an odd number.
First half. Unfortunately, that means there is one. I can just point at and say it's in the middle all by itself. 19. So there's 4 before it, 4 after. So at 19 is the Q1. Then do the same thing. Second half. Middle or median of these, there's 9 of them. 55 has 4 before it, 4 after. So that is the median of the second half. That's the.
So those are the quartiles. And it's breaking the numbers up into 4 groups.
That has roughly the same number of data points in each group. You can see here when I do that, I got 4 before here, 4 in there, 4 there, 4. Breaking it up into 4 groups of 4.
Now that number can be slightly off depending on if you have even or odd numbers. But it's roughly approximately 4 even groups.
Anyway, if I go back up to 13, that one now. 13 isn't asking us to find the quartiles, they're asking some other questions related to quartiles. Thirteen says a recent survey by the U.S. Census Bureau determined that the median monthly housing rent was 635. Median 600. If the first quartile of housing rent was 480. First quartile. 80. And they said, find the percent of monthly rents that were following values, more than 480. So first of all, kind of draw a picture here. Idea is you've got all these rents, all these different numbers. Imagine that they're all listed out from smallest to biggest. The median, right here's the middle. Second quartile. And then we have, there's some particular value that is the median, and they say it's 635. We got some particular value here. It's the first quartile. They say it's 480. We have some other number here that'd be the third quartile, but they don't tell us what it is. But we don't need it with the questions that they ask. Anyway, part A wants to know what percent is more than 480. So the idea is we got all these data values. 100% of them are listed here. Median splits it in half. 50 before, 50% after. First quartile separates the first quarter was 25% from the next 25%. But if we want to know how many are above 480 altogether, that's the first quartile. So there's 25% before, 75% after. 25% there. That leaves 5% afterwards. So the answer to that question is 75%. So more than 480, 75%. Less than 630, 635, less than 635. 635 is the median. It's in the middle. So it's splitting it in half. 50% below, 50% above. Fifty percent below. 50% above. They're asking though,
Less.
below. 635, 50%. So that's what's it at, 50% below.
And then part C, in between.
480. 635. Four eighty is first quartile, 25% below it. That's the median, 50% below that. So in between these two would be 25%. 50% below, 25% there, that leaves 25%.
$50 there.
25 there.
All right, so that finishes this section. Good pausing point. So I'll stop here for today. Tomorrow we'll move on to the next section, more of this stuff. Up at a 35. So anyway, that's all for today. Have a great rest of your day. See you tomorrow.